We have some change from the National Research Agency in France, especially in France, with the France 2030 initiative, where original research topics are now expected. We can see advanced material and processes, integrated intelligent system, programmable manner, material design. We can also see some specific topic at the international level, for instance, at the Horizon Europe or NSF, where the focus or the expectation are on augmenting, let's say, product functionality, making system intelligent for the configuration, developing physical product with digital twins and Industry 4.0 or even 5.0. I just integrated into my slide a picture of the HIP cycle of from Gartner Institute from 2018, where 4D printings were at the innovation trigger stage. We can think that this technology is now at the top of the curve, and we will start a kind of disillusion stage. So we have a lot to do in order to increase the TRL level of the technology, and we have also to find disruptive application in order to demonstrate that this technology has a future. For all of this reason, my research group and I have developed effort in advanced design methods and digital thread. We also are focused on advanced fabrication techniques of general shape changing mechanism to deliver to create transferable system compatible to human usage environment. So 4D printing is based on additive manufacturing. So additive manufacturing has been introduced 40 years ago. First patent was a French patent by a friend of mine, Jean-Claude André. And with this technology, the complexity is free. So in terms of shape, functionality, hierarchy, and materials, we have approximately 200 kilo articles with a growth of 14% a year. And now we can see that the technology is matured and the research is incremental. And 4D printings is approximately 10 years old, funded by Tibbetts, Martin Dunn, Jared Shih, even Kevin Gehr. And this technology is totally different since the complexity is augmented. We have 2,500 articles and a growth of 44% a year. The research is interdisciplinary and disruptive, so which means a lot of challenge, even in terms of application. What I can also observe from a system point of view is that the design efforts were made so far on mechanical system, mechatronic system, over the last decades on connected objects and cyber-physical system. And what we can see from the research agency is much more is expected from a smart system. And we can also give an estimation about the capability maturity model for each system. Most of them are at the top of the capability maturity model called optimizing, and smart system is still ad hoc. This normal technology is still developed in the labs. We can also highlight some industrial initiative toward smart system in the car industry with BMW concept car. We can see some tires from Hankook, some shoes, even some stands. And through this case study or through this innovative concept, we can see that what it is expected is systems that are adaptive, reconfigurable, deployable, and transformable. I tried to sum up 4D printing into 2 slides to sum up the research efforts. So the main efforts are focused on single material 4D printing and material, which means that we use only one head, let's say, and we print the smart material, and we can exhibit a shape change by playing with the printing path or both with the polymerization intensity. Another strategy is multi-material 4D printing in order to improve the mechanical performance of these soft materials. The idea is to combine active and inert material into a single structure. Here, I just put some material distribution category from sandwich, bilayer, special pattern, gradient, and digital, to which I introduce some example. You can say we can see here that the idea is to properly distribute the material into the structure in order to achieve original or specific shape change. I also try to understand the current state of smart material in terms of mechanical performance. So I draw some diagrams that explain on the x-axis the main category of smart materials in terms of SMP, SMA, piezoelectric, hydrogel, IPMC, LC compared to muscle. And the idea is to put effort in order to increase their Young modulus, to reduce response time, and improve their efficiency, even their force generality. And what we can also highlight is the limitation related to the process. The process of smart material elaboration is very hard for non-expert to develop smart materials. They are not available. They need the tuning steps. They have limitation in terms of functional fatigue. We have also some limitation in terms of additive manufacturing process, in terms of material process couplings, multi-material capacity, anisotropy induced. That is sometimes an advantage for 4D printing. And also another important aspect is the third pillar of 4D printing, I mean stimulation. So we have to consider the temporal effectiveness. We have also considered that the stimulation can be inside the structure, can be local, and we have to consider the place of the stimulators. So for all these reasons, I try to build a research roadmap from a design perspective, where the main objective is to design systems, smart systems that make sense and meet use. And to do so, we have to consider many facets, if I may say, multiple material, multiple domain, material chemistry, physics, engineering, robotics, manufacturing, multiple additive manufacturing technique, multiple physics and energy, multiple scale and temporality. We have to consider also multiple function and multiple world. So most of the effort are made on physical world. I'm working also in the digital world. We have to connect this world with the cyber and the social world in order to improve interaction between the user and the object. And to propose something strong, we need to put efforts on knowledge, model, method, and tools with specific reasoning procedures in terms of geometric optimization, multiple representation, semantic AI reasoning. Through symbolic AI reasoning, I mean ontology, I mean providing qualitative reasoning. We can also address connectionist AI reasoning through machine learning, deep neural network, and biomimetic computing. And the last one is to have some target application in specific application sectors. Without this last part, any design method can be useless. So I try also to sum up the contribution. I try to sum up the contribution, or let's say the aspect we have to cover in design. So we have to, if we want to design for 4D printing, this means that we have to design for material assembly. We have to design for additive manufacturing. We have to design with stimuli, with smart material. We have also may provide some sort of solution in order to design for transformation with AI, for instance. And we have also to design for performance. So we have a lot of challenge. Probably I will have a lot of work during the next 3 decades. So in terms of knowledge, what we have done over the last 3 years is building a kind of knowledge base on which we can capture any kind of knowledge from experiments, from simulation, from literature. And the idea here is to structure the knowledge at the object level and for various purposes in order to provide guidance, assistance, recommendation to all users involved in 4D printing process. I mean, product architect, material expert, product designer, and even a process planner. And this ontology, this knowledge base is also driven by underpinning theories like 4D-dimensionalism, 3D-dimensionalism, in order to understand how an object can evolve over time. I just put some part of the ontology. So the ontology can be understood as a knowledge graph. I mean that the blue circle represents the knowledge, and the connection between the blue circle means the semantics. With this kind of graph, we can understand a scientific domain. And the red circle means the data property, and the purple circle means the instance. The instance comes from what you are currently, what is published, what is experimented, what is simulated. Based on this ontology, the idea is to capture knowledge, but the end is to reuse the knowledge or to propose knowledge to any kind of new project. So the idea is to develop a new approach called semantic multi-vector space model. And the idea is to compare, for example, a specific need or a specific target with experiment capture in the ontology. For this case, we decide to provide a reasoning recommendation procedure in order to propose smart material distribution into a structure. So starting from a solar panel development issue, the designer may want to apply a specific energy, may want to apply a specific timeline, etc., etc. And this term, this knowledge is initiated into the process flow, and how reasoning is able to provide what is the experiment that may fit the best with what it is request. So we implement a specific in-house code into a Rhino grasshopper environment. In terms of models and methods, we also use a voxel-based model in order to simulate very quickly smart material distribution into a structure. The idea is to get very quickly an answer in order to get the design of the structure. So we use from a rough geometry, we're able to discrete the geometry into voxel, and each voxel, each center of voxel is connected to each other in order to construct beams, and we put the material modeling onto beams, and we are able to simulate very quickly this kind of behavior. This simulation tool has been implemented into a Grasshopper plugin called VoxSmart, and we can edit the geometry in terms of voxel. You can apply multiple smart material inside. You can also simulate, and let's say in a couple of seconds, you can see the shape change. Due to time reason, probably I will shift this movie, but during the question, I can show the movie to everyone. By knowing how a shape change can occur with a specific stimuli, the idea from a design point of view also is to provide solution for inverse design problem. So from a design point of view, what we have is we know the initial state, we know also the target state, but we are not able to know without any simulation what will be the smart material distribution with active and passive material. So the idea is to use genetic algorithm in order to compute and find counterintuitive distribution. So you can see on the right parts an example of what we have done with the software. So we have simulated a spatial pattern distribution, and the distribution that seems to be weird has been computed by our software. We also try to make some kind of topology optimization. The idea is to integrate void into the structure. Why integrating void into the structure? In order to improve the efficiency of the shape change we want to achieve. The idea is to, if I minimize the shape, the smart material, for instance, I will also minimize the use of energy stimuli. And what we have done here is we have integrated a third material into the genetic algorithm. And this third material has been considered as void or without small property. And we get similar shape change with less materials. So with this kind of progress, we have, from a digital point of view, we are able to build any kind of structure. We can simulate any kind of structure, even with dissimilar material. But if you want to print them, we will have some difficulty. So we try to investigate different multi-material manufacture strategy. We investigate multi-head DIW with light irradiation. We also develop hybrid DIW and FFF to print multiple material. We also investigate robotic assembly of voxels or even polycubes. And we have also patent pending technology that is still secret for today, but I hope that I will be proud to present technology next year. So from the left to the right, okay, probably we will be able to have more freedom in terms of material combination, even in terms of dissimilar material, for example, between polymer and metals. An example of the different machine we built. So we built a multi-head DIW on a CNC machine, and the multi-head is use a barrel device. So this means that we can rotate the DIW. We put also some UV on this specific head. We develop specific code into the Rhino Grasshopper in order to control the machine. We also upgraded a multi-technique and multi-material 3D printer. This means that on the gantry, we put different heads from gripper, DIW, FFF, even UV. We use an American machine called iRail 3D, the open source 3D machine printer. We use also S2000 Omnicure UV curing system with different heads. And the idea is to combine different materials together. But each state generates a lot of not a limitation, but complication. We have to find appropriate parameters. So building such kind of machine require a kind of digital twin. So we develop a software in order to control each head and also to ensure a closed loop in order to have a real-time adaptation. This means that the system will be combined with a camera in order to receive data, provide digital image correlation. And with this kind of software, we will be able to control the printing parameters in a single print. We also investigate topologically interlocking voxel assembly. So let's imagine that with our software, we are able to compute a material distribution, which is similar to the part I presented here. And with this part, we are able to partition the structure in terms of material, and we will extract the blocking relation in terms of translation. And based on this blocking relation modeling, we will be able to generate automatically interlocking polyvoxel assembly computation. And then, based on this interlocking polyvoxel, we then generate the assembly sequence. I mean, the order in which the part require to be assembled. So it's a kind of strategy between 3D printing and assembly, which we can call it 4D manufacturing. An example here is provided with this beam. We have two materials with a specific distribution which come from the simulation. We extract the homogeneous subassembly in terms of material. We then generate interlocking voxel with key interlocking part. The key interlocking part here means that the part we ensure that all voxels are blocked. And then we assemble them together. We also try to implement the technique from the simulation. So we print thermo-responsive hydrogel blocks with DLP. We also print passive elastomer blocks with material jetting polyjets, and we perform the assembly with manual procedures. So we can see that the shape change through a thermal simulation. So I don't know if I have time to present the video. I have to accelerate, probably. Okay, go ahead. So in terms of timeline and roadmap, I draw on the x-axis the timeline about what is achieved today in terms of contribution published, what is currently addressed by my research group and my PhD students in terms of knowledge, model, method, and tools and equipment. So we are in terms of model, we are working now on large language model like ChatGPT. And we use also natural language processing in order to capture all the knowledge of the community. We are working on multi-scale voxel-based models, smart material distribution pattern. And the idea for example, for a knowledge point of view is to extend what we know, not only at the object level, but on the material level, but also at the system level, or even in the natural level. In terms of model, the objective is to augment the complexity in terms of geometric and structural, physical model and data representation. And for method and processes, we are working on augmenting the efficiency of our algorithm with AI through physics-informed neural network, for instance, but also with the support of symbolic AI. And in terms of tools and equipment, we're working on increasing additive manufacturing capabilities of multiple scales and multiple techniques. And we also currently developing digital tools. This is my last slide. So I'm PI of recently funding projects by the French initiative. The project is called Artemis, and it means accelerated discovery and development of smart material and structure with 4D printing technologies. So we received 1.5 million euro over 48 months. The idea is to integrate AI, or let's say to develop computational intelligence, which combine material and design informatics with machine learning, and connect these innovative bricks to numerical simulation, physical experiment, published article, online database, whatever, and use this kind of technology to explore and discover new smart material composition in terms of shape memory polymers, shape memory alloys, and LCE, but also to work at a upper level in terms of structure. And the idea is to try to explore and discover material distribution, discover the appropriate material distribution pattern, work on the behavior on the interface and metamaterials. And I'm also PI or special interest groups that will be available in France in 2024. This special interest group is supported by the CNRS and is on smart matter transformation and 4D printing. So all this latest information are based on 2 books I wrote with my friend Jean-Claude André, and I hope that this kind of initiative will help the 4D printing society to be better organized and will play the role of a bottom-up strategy, or even can be generalized to any kind of initiative in US, China, whatever, Singapore. I would like to thank you for your time, and I will be glad to respond to any kind of question.